So this is a report that this is a scientific or technical talk about a piece of music that I did in collaboration with Carrie Hagan. And so what I would like to do is play you just a 30-second extract of the piece of music that we're talking about to contextualize the theory. So if this movie plays, we will see, yeah, there we go. Right? So I played that first so that if you don't like what you hear, then you can just read your email for the next 15 minutes, and then there's a very good talk coming up next. So what I want to do now is just describe what where those sounds come from. So as you can tell, you're not hearing guitar and clarinet sounds. We're just taking the sound and turning it into parameters and then using it to parameterize a synthesizer that's doing something unrelated to guitar and clarinet. The collaborator, by the way, is Carrie Hagan, and what you saw there was actually a networked performance between her studio in Ireland and mine in San Diego, California. So what I'm going to do is jump into the theory quickly, and then after theorizing a little bit, then show you what the patch looks like and how it acts that I use to realize this. So the first thing I want to say is that you can think of oscillators, actually everyone knows this, but you can think of just about any kind of circuit as a flow through a state space, which is to say it's a system of ordinary differential equations, right? And thinking about it geometrically can sometimes be a good way of understanding how the system is going to work if the dimensionality of the space is sufficiently small that you can feasibly think of doing this, right? And so, for instance, a pair of oscillators in which one oscillator is soft synced off another oscillator, this is an example, right? You can describe the state space as being the phases of the two oscillators, and depending on the phase of the vertical oscillator here, in a certain region of that, the phase of the horizontal oscillator is pulled toward the whatever you consider zero phase. And then that causes the vertical oscillator to synchronize or to be a synchronization source for the horizontal one. And then you can get these interesting non-periodic behaviors. And this has been done practically since, at least since Buchla was building his wonderful dual oscillator module back in the 70s, right? And thing about dynamical systems, if you are using them as an effect, then of course you're driving it with a signal and it doesn't ever fall dead, we hope, right? But when you're using them to make, as synthesizers, then you have to worry about one very fundamental thing, which is what happens when you've got an absorbing point in your state space. Then your sucker just stops oscillating, right? So you can't just write any set of differential equations out in the world. You want to come up with a set of equations that you know is going to do something reasonable, at least keep moving, right? In the case of the oscillators, not as I've drawn here, by the way. In the case of the oscillators, as long as everything is going northeast, that's to say, as long as all of the frequencies are positive of both of the two oscillators involved, the thing can never get stuck, right? Now, the disadvantage, or a disadvantage to this particular example is that it's topologically messed up because it's a torus instead of a simply connected space, right? And that makes it harder to do certain kinds of analysis of what the thing might do. So the question now is there a nice, simply connected space with a lot of inherent symmetry, or a lot of symmetry, that allows you to think about the behavior of the space in a way that would allow you to try to design sounds with it? And my proposed answer to that is let's go for the space of unit quaternions. This is a three-dimensional space, not a two. That makes it harder to think about. Okay, so it's a three-sphere, which is to say it is a sphere that would normally be embedded in 4 dimensions if you wanted to look at it as a sphere, but being three-dimensional in our imagination, the easiest way to think about it, the state space of the sphere is to talk about the lower and upper hemisphere as being three-dimensional balls. So here is my representation of the state space of unit quaternions. I'm going to go back and say something about how to be a unit quaternion in a second. So the quaternions are something. Oh, let's just go there. Quaternions are things like this. It's a four-dimensional set of numbers. The numbers, unlike complex numbers where the complexifier is this number I, the square root of -1, you get 3 square roots of -1, which you call I, j, and k. Each one of them squared is -1. They anti-commute with each other, and they do all kinds of stupid stuff. And you can also represent them as 2 by 2 matrices of complex numbers. And you know the AB minus BA, that's the same matrix as a complex rotation if A and B are real. But A and B being complex, you can make the same kind of matrix, although you want to conjugate the bottom row of the matrix if you do this. And then you get a nice, still multiplicatively closed and additively closed set of 2 by 2 complex matrices that have good properties, right? Okay, so this is the set that we're interested in, and in particular, we're interested in the points where the norm of the quaternion is 1. That's to say, not all possible A, B, C, D quadruples, but only those that the sum of whose squares is 1, right? And that the whole set of quaternions is in fact a set of rotations. Rotations follow or combined with dilations in 4-dimensional space. But if you deal only in the unit quaternions, the well-behaved ones, you're only talking about rotations, and you have a 3-dimensional set of rotations of a 3-sphere, which, by the way, has a 6-dimensional set of rotations in all, so this is a subset of all possible rotations. So this is just to confuse you some more. So now, if you think about these unit quaternions, you can think of them 2 ways. They are, each one of them is a rotation. I mean, each unit quaternion is a rotation considered as a transformation, but it is also a point in the space that it is rotating. The space is 3-dimensional, but it is a only 3-dimensional set of rotations, okay? Now, so how do you oscillate on this thing? Well, you can do exactly what you do with complex numbers, which is to say, take the complex plane, take a unit complex number, and just raise it to different powers, which is taking the unit circle in the complex plane and turning it around and around, you get an oscillator, great. In the quaternions, you can do that, and in fact, if you decide to set the frequency to be 1 plus some small number times I, which is one of the, let's see, where did I put I? I put I front and back in these things. So if you rotate in the I direction, and if you start at the phase point 1, then you will come out from 1 to I, so I don't know how to point here, but you'll go from 1 to I, and then, oops, now we got to the boundary of this sphere, which we identify with the boundary of this sphere. We go from I to -1 to minus I forgot the minus sign. And then we're minus I, and then we come back to 1 here, right? Okay. Meanwhile, same frequency, but we'll start with an initial phase of J, right? So phases and frequencies are the same thing because the rotations and the things rotated are in the same space, right? Start with J, well, you start going in the K direction, and then you start going toward minus J, and then you start going toward minus K. So now imagine a rotation, some sort of continuous rotation of this thing, which does both of those things simultaneously, from 1 to I to -1 to minus I, from J to K to minus K, and then everything in between is sort of a twist that's halfway between going straight that way and going around this way, right? That's all you have to think about. Now, that's one possible frequency, right? There's a frequency which is a combination of 1 and J, which would also be a unit quaternion, and which would rotate us in the 1J plane and would rotate us in the IK plane. In fact, there is a 3-dimensional set of possible frequencies, any fixed one of which would take this 4-sphere and look at it as a product of two spaces, two-dimensional spaces, and do the same speed rotation in those 2 spaces. Okay? So far, so boring, right? Because if you play that, you're just going to hear a sinusoid. But now, what you do is this. You say, well, okay, any one of those paths, by the way, spends exactly half of its time in the upper hemisphere, which is this one, and half of its time in the bottom hemisphere, which is this one. So that's cool, because what that means is that if you give the oscillator a frequency which you believe to be fixed, there is a boundary that it is guaranteed to hit twice per cycle. And so you can use that to fix it so that the thing can't do anything too boring, because as soon as it gets boring, that means it's going in a circle, and every boring circle then hits every plane, so just make it change whenever you change planes, and then you will get something that can't possibly just behave itself circularly, right? So, 3 minutes left? Okay, oh, I'm going way too slow. Oh, well, let's go to the patch. To hell with this theory stuff. Actually, I will, let me show you a path. This is nothing but just taking two pairs of hemispheres, upper and lower, like I described, and then J is positive and negative, those two hemispheres, and just setting 4 different quaternion frequencies, one in each quadrant that those things mark off, and then you get a thing like this, right? Okay, now I'm going to play it, or try to. So this is my little patch. Oh, and it's doing something boring now. There we go. So here's now just, all right, that's fine. Oh, what's going on here is I just have one fixed frequency, which is MIDI 70, and then I have coefficients to add to the frequency in I, J, and K for the upper hemisphere and for some other hemisphere somewhere, right? And that's all, so I'm going to specify one fixed frequency and 2 quaternion frequencies by which you kick it to one side or the other, depending on where you are. And then you get all the interesting behaviors. Wait, I had 3 minutes left and now I have 4? Okay, all right. Oh, right. Okay, so nasty clarinet sound. So now, you can sort of get a sense of what you might change to get a different change in the sound, but there's still a lot that's just sort of left to exploration. Okay, that's my clarinet. It's not a very good clarinet. Here's sort of the, oh, come back here. You hear that? So different limit cycles, depending on what the phase was when you started in. Yeah, and well, I'm not sure what to do now. Okay, so let's go try this one. Right? All right. Okay. Now, if you're like me, this is cool, and you and then you just sort of play with this for hours and have fun. Yeah, that's pretty much the talk. We have time for questions, but I'll show you what the patch looks like a little bit. Quaternion, just have 4 delay lines of 1 sample each, and then just mess around with the numbers until you get what you want the next thing to be. I'll let you enjoy that for those of you who want to analyze it, and then fish for questions. Yeah.
So thanks. We have time for non-linear questions.
By the way, there's a fair amount of theory in the paper about how you actually exploit the symmetries to try to keep the parameter space under control and stuff like that. Yeah.
I missed what the deal was with the clarinet.
What was the deal with the clarinet?
Yeah. The clarinet enter into the patch. I just can't quite.
Oh, I just named it clarinet because it sounded like one.
Oh, gotcha.
That's what computer musicians do. You hear a sound that is vaguely reminiscent of an instrument like that, and you name it for the instrument. Like the FM clarinet from '73, right?
Hi, thanks for the talk, very inspiring. I see you have 4 outputs, I guess, for each component of the quaternion. At least there's 4 volume bars on your patch.
You mean up here?
Yeah, 4 meters on your patch.
Oh, I'm sorry. Yeah. So, all right, I didn't say something important, which is what do you want to listen to when you're going to play these things, right?
Yes.
So in this case, what we're hearing is actually the phase of the oscillator, the I, J, K, and 1 component of the state, momentary state, right? But you could make any other function that you wanted to. In fact, if you wanted to do something more irregular, you would like have a step function that was 1 in some region of the sphere and 0 in the others, and then you would get constant pulse width mod, right? So yeah. So don't be afraid to apply functions to this. Yeah.
Could you choose like a projection to, if you, let's say, if you want to have single dimension output?
Yes. In fact, if you just, these 4 things are in fact 4 projections, right? But you could project onto some oblique plane too. The deal is it doesn't sound much different depending on which direction you project on. It changes the amplitude and the frequency balance, but not the overall quality of the sound. So one thing that you could do, in fact, is just take these 4 things and send them to 4 different speakers. What you heard, I believe, was just the 1 and I signals, and I dropped the J and K signals because, 2 speakers.
I think there was one question.
Okay.
Yeah.
Yeah, I should have said that, in fact.
Okay.
Yeah.
Yeah. So.
Yeah.
Thank you. I was wondering about the connection with the video we saw before. You said you control the synthesis parameters using the sound?
Using the instruments, yes, right.
Yeah, can you explain a little better how?
Oh, yeah. Well, you know, Carrie and I did our 2 different instruments completely differently, right? So she does a lot of stuff with stochastic processes, and she was actually measuring mostly the envelope and the upper and lower frequency content of the clarinet, and then simply having different regions of behavior depending on what percentage of the time she had recently been playing in what register and things like that. But also being careful to make the volume of the sound always follow the volume of the instrument, so that when she blew, something happened, and when she stopped, nothing did, right? Also, she did some key clicking, and so she had a way of analyzing the sort of pointillisticness of the sound, and she used that to have 2 different parameter regimes. Right? Me, I had a guitar with 6 pickups on it, and I did something really stupid, which is I just came up with 6 presets that I liked, and each string just, whichever was the loudest string was that preset, and then the fretting on the string was transposed it. And that was it. And then, of course, the volume again. Envelope follow the guitar, and then have that control the envelope of the output. Yeah.
Thanks.
Yeah. That's it. Everyone's going to go read the paper now. Right?
Yeah.
Or read your.
There is a last question.
I didn't, and I should. Yeah.
I think you mentioned that we can download something, but
Did I?
in the
Maybe
paper,
I did.
yes.
I have to look. I barely remember writing this paper and don't know what's in it. So if I didn't, I will. But and if you look for it and can't find it, write me an email and remind me, because I intend to put this out. Yeah.
Okay. Great.
All
So thanks, Miller.
Thank you all. Yeah.